our next speaker, I'm very pleased to introduce Lucas Winter from PTB Berlin. And he's going to be talking about the open source MRI from dream to reality.
Yes, thank you very much, Clarissa, and thanks, Tom, for the nice presentation. I try to not be too redundant in my talk. Just one thing for the field mapping. So this is this cozy measure that Tom also has, and there are a couple of versions. The problem was that the electronics was not reproducible because one part was not available. But what we actually did, so it's not months, but it's actually nearly finished. So hopefully this Friday we will have a first test run. It looks a little bit less open source like, but more PTB like, more classical, quadratical. But it's nice setup, and with that, then we will be able. All the people that have one, we will be able to work together on the software, which is, I think, pretty cool, because then we can add some more functionality to it. Okay, just wanted to say that in case anyone is interested. But I wanted to actually talk about the open source MRI from dream to reality, and I have nothing to disclose. So just want to make sure before starting, and this is my classical slide, what does open source mean, just for everyone to be on the same page. So open source software is software that can be freely accessed, used, changed, and shared by anyone. And same for hardware, you have the right to study, to modify, to distribute, and sell. So yes, you can sell these designs, the right to make. And basically these rights to freedom are granted through open source licenses. So two things: if you want to make your stuff open source, means that you share everything publicly somewhere on a website, and you add an open source license, and then it's open source. And then there are two links that can help you with choosing the licenses. This is the Open Source Initiative and the Open Source Hardware Association, for example. Okay, so now having this a fancy title from dream to reality, I will want to share a little bit my dreams with you. Yeah, and not all of them, of course, just the MRI related dreams or healthcare related dreams. Just to see, to put it a bit in perspective, what Tom showed, what the slightly bigger vision is that we all have in this community. So when I think of dreams and I think of science, then there I dream of reproducible and resource efficient science, so that we basically easily build up on our predecessors and maximize our output per resources invested. Yeah. When I think of healthcare, I dream that technology is transparent, that we all are able to evaluate it and further optimize it. I dream of easy maintenance and repair manuals. So for example, if we donate devices into low-income settings, they can be kept operational. Yeah. I dream that innovations that we are all creating are easily translatable into products, and that the decisions are not based on factors like a profit, marketing, portfolio, whatever, but are really just based on healthcare outputs. This would be fantastic. If the costs of medical devices could be optimized to remove any unnecessary overhead. I would like medical devices to be easily comparable. Yeah? So for example, thinking of MRI, that the diagnostic or further therapeutic outcome is quantifiable. Yeah, this would be great. In terms of access, I dreamed of every patient on this globe to have the same opportunity to access a critical medical technology. When talking about community, I dream of our community being inclusive and diverse in its true form, so that we really represent the diversity we have globally. And this also then impacts our scientific and clinical actions. And I dream of focusing on collaboration instead of competition, because this would also mean to focus on content and progress instead of the ego. Would be nice. And then last but not least, I dream of easy and free access to information to understand complex systems such as MRI. And through these complex systems and complex problems that we have, to basically cure you and me. Yeah. So starting off with this dreams, and I will not talk about any problems that we have. So there are a lot of challenges, etc. And just to give a reality check with this, let's say, hippie dreams that I just mentioned, I would like to show you what's happened so far and where we are going, and what are the next steps. So when we look at the timeline, it started actually very simple because just to formulate the idea that we need an open source MRI scanner, and there was basically nothing out there yet. There was some software work, but on hardware side, there were very few modules. But then it picked up pace somehow, and after a couple of years, there were first prototypes, not completely open source, but does not need to be. It gradually evolved. And then in the last 1 or 2 years, we now have full open source MR systems. There are also some tabletop systems that I don't have time to talk about in this presentation. So I just pick these two. So one is the one that Tom was showing, this project that we're working on is this OZ1 system. And one more recently joining the club, which is super cool, is this Zeugmatron Z1. I hope I pronounced it correctly. And this was a recent hackathon that happened in New York by a lot of people and a lot of institutions. So this is super nice, and it's interesting to see what happens next. But let's just check first what these two systems look like and can offer. And I will start with the more recent one, this Zeugmatron, because the OZ1 I can then, it fits a little bit better into the flow of the presentation to do it afterwards. All right, so this was, here you can see a really nice animation of all the components, magnets, cooling system, gradients, RF coil, RF coil shim inserts, etc. And this is was created during a hackathon. This was actually in October this year, so very recent. It took 4 days only to build the system. 52 participants, 16 institutions. It's a Holbach design, 43 millitesla field strengths. You have 3D printed scanner parts, which is nice because you can reproduce it more easily than being dependent on some external production facilities or companies. Then you have a cooling system, passive and active shim options, and electronics. It's a red pitaya with a Marcos interface, and then a GPA FHDO for the gradients. And Marcos is also PyPulsec compatible, so you can also run PulseSec sequences on that. And a Python-based graphical user interface. And here you can see some nice images. So Clarissa is also here in the front, and this is great. In 4 days to build such a complex scanner, and then the first image was acquired recently. So if you're interested in that, there's more actually in the session 2, transparent innovation. So have a look at the presentation, and then you get more details on these systems. And resources and software for that will be uploaded to this website here, so mri4all.org. So please do have a look at that. Yeah, and the scanner that Tom was already mentioning that we are working on is this OZ1. I just called it version 1. That was shown, so it's around 20,000 material cost. It's a relatively portable system, 50 millitesla, and then there are these 3 different systems at the moment in Leiden, Berlin, and Uganda, and some images of the head, phantom, and knee that you can see here. This was also the scanner that we brought last year to London, so packed it up in a small van in Leiden. Then over the ferry, some setups from Tom, and then we had the build your own open source scanner session, which was quite popular. And you can also see in the front, so there's Kristen. So somehow this build your own open source scanner team is back here as well. So Kristen will talk afterwards. And this was a very nice session, created a lot of interest, and demonstrated also a little bit this portability of the system. Okay, so now where we are at the moment, we're actually working on the version 2. Version 2 means it has to be more robust and many other things. So we also had recently a workshop on that. It was less practical, so we didn't build anything. We just had a lot of talks. if you want to listen to them. It's a combination of talks and discussions on different modules and components of the system, with the idea to fix some technical specifications. So this has been done. Some discussions, ongoing discussions, is on Matrix. So this is what Tom mentioned. So our Slack channel will be disabled at some point. So please join this one here. We will also have some updates on open source imaging on that. But yeah, like with many other things, we are way behind. So just be patient. And if you want to join, just copy that or contact me. Then you can also find the slides here. The repositories are currently here in GitLab. Most of them, if not, we will link from there to the other places where some sub-modules are located, either software or hardware. This workshop was organized from within a project that is actually testing a little bit this concept of open source medical technology. So we built an open source medtech lab within a hospital, and one of the scanners we will also place there. And this is to explore also a little bit this concept of open source medical technologies. And this is also the idea of this project. So it's to eventually land in the clinics. And I think this is where we can all create these benefits and link to these dreams that I showed in the beginning, because I think that's the best strategy to have open source tools to get there. And when we look at the imaging performance of this 50 millitesla system, so Tom showed these images as well, and then you can compare them to some more clinically relevant or what you can imagine could be more clinically relevant. It's just a nice paper from the Hong Kong group, which actually show some tumors at 55 millitesla, so very similar field strengths, and then compared to 3 Tesla. So you definitely have some information there. And of course, you can argue or think about what is better in the end, which field strengths. Yes, we can still have these discussions. But actually for many patients globally, this is not the question, because they are happy if they get whatever image they can get. Yeah, so I think it's a first good step, and this is the direction to go. And if we have such an affordable system, I'm pretty sure that there will be many innovations and ideas on how to use it clinically. Yeah, so there's a lot of potential here. Okay, having said that, we started recently with also quite a lot of partners, a project to actually bring this closer to the clinic. So we are building a couple of MR scanners that is based on this design, that are fully open source, but that they're also fully characterized in terms of uncertainties, etc. We will compare them to other commercial low field systems and mid field systems in terms of image quality. Test some sensors and some other techniques to improve these systems. But one thing that I think is really interesting and important is that as part of the project, we promised to provide documentation for regulatory approval. Not all documentation, we cannot provide all documentation. There are certain things like post-market data, which we are not a producer of MRI equipment, we cannot do, but there are a lot of stuff that we can do. And this is something that we want to provide this documentation, which is also not publicly available. And this would be like a fantastic blueprint for other medical devices or similar medical devices. So the hope is that actually we reduce the hurdle, how we can get from this research prototype to a more clinical device. And then it's easier to get products on the market that are then hopefully more affordable. Yeah, so this is what this project is about, and I will show you some of the components. So this first magnet, or this version 1 magnet, will be in the next version a little bit shorter. This is just that the head fits better in the ISO center. So you can see that here. We started already, we haven't finished that yet, but we started already to assemble it. There are other things that will be a little bit easier to rebuild, and this is, you can see it, for example, in this image here, that there are screwable lids, so there will be no glue used. So you can also reuse the magnets if you want. They are not cheap. If you make mistakes, it's not a bad idea to be able to replace them in a different configuration. There will be also less screws, so this will hopefully be a little bit faster and easier to rebuild for others. A gradient coil design, we don't have such a fancy animation, but at least it's rotating, so that's already cool. I'm happy about that. So here's a gradient coil that is designed with the tool CoilGen. CoilGen originally from Freiburg, Philipp Amrein, and it's a MATLAB-based tool, but in the meanwhile, someone already converted to Python, so you can also find the Python version for it. It gives you the wire pass on certain targets that you define, and then you can easily translate this, because it comes out as an STL file. You can translate this into a CAD program and then create some former that you can then 3D print, for example, to make your gradient coils. This is so far only in simulations or in this design file, so we haven't built this yet. We need to build the magnet first. Okay, electronics, or in particular more amplifiers. So the grand amplifier that Tom showed, this is great. We will use that. There will be just tiny modifications made, but in principle, the design will be used as is. The power amplifier, yeah, it's a little bit too overpowered. And probably the most annoying part about it is that it's too loud in its current configuration due to some the terminal management that's been done at the moment. So this will be worked on. So there will be a lighter version of that. And then nice thing that's also happening is that basically also companies got interested in this more open approach of hardware, and this was this Bartel RF amplifier that will be partly open source and maybe at some point even fully open source. But this is also nice that there are companies getting interested, because in the end, not everyone wants to rebuild these parts. But maybe some people would like just to buy it off the shelf, but it's still be able to modify them or repair them, etc. So this is interesting. Console, here is a classical. This is the part that we built up in Berlin, but it's a classical red pitaya combination with an Okra 1 board. And a much nicer and cleaner and a version that runs also through the safety tests, is already being built by Markus Priya and Benjamin Menkuc in this combination, and then we have this as the console for this MRI system. The software is Marcos, was also mentioned. This is PulseSec compatible. Another option to run this is using the Physio MRI GUI. This is by the group from Valencia. And they also did some nice in vivo images already with their system. So you can find all information for this under this link here. So more general, coming to the system overview, this is still work in progress, so some things might change, but the strategy is we have modular hardware components and well-defined interfaces, so that in the long run we can exchange components. So if you want to change the gradient amplifier, for example, we can do that without doing major changes to the overall system. Similar with the console. So we also work on different console version that's a little bit more expensive and can do scientifically explore more stuff, so it can be exchanged. But at the same time, you still have some safety protocols like SAR monitoring. You have, for example, a coil feeder panel with a coil code, etc. So this is more or less our idea on how we want to build it up. And then having this in there includes also having log files of knowing which system components the system currently has. That can be then transmitted to the external software that actually runs or defines the pulse sequences, does the image reconstruction, etc. that needs this information. and that's also we can work better together when there are bugs, etc. If you just send log files and you know really like what's your system is containing. Okay, similarly for the software, also work in progress, but just that you get a glimpse of what we're working on. So which data formats are being used, RICO engines, so compatibility, for example, to ISMRMRD format, and then you can do reconstructions with Gadgetron or BARDs. You, of course, need some DICOM engines, and in the end, ideally, some compatibility with some external PAC system. So there are still a couple of things to be defined. This is more like a general overview, but there is also already software available that can do many of these things. So this is, for example, software is called ScanHub that we're also planning to use. And again, in the input, you have, for example, something like PulseSec. Then you have your MRI system. At the output, you have something like ISMRMRD, which you can connect to your reconstruction pipeline. And have some visualization, and then maybe another post-processing pipeline that is needed. Okay, all of that works only if documentation is somehow done, and this is really challenging. But here, what we are trying to set up is to work a lot in repositories. So currently in GitLab. So we're trying to under this link, trying to at some point pool all the information, even though some of the again submodules maybe are on GitHub or on different location. But we try to pool on information here, mostly Markdown, because that's easier editable, and also you can understand who made the edits, etc. That's also important for the documentation part for regulatory approval. There are fantastic tools in there, project management tools like issue management. So you can, for each module, you can write in, okay, I have this bug, or I have this idea or upgrade or whatever. So this is fantastic. Versioning, there's a versioning strategy with which branch to work on, and then you have a release at a certain version, and at some point, and this is this yellow branch here, if the release is mature enough, then this will be forked into this documentation pathway of something that goes more towards regulatory approval. And this will be then fixed. Yeah, so this will not be touched anymore. Just so open source, an open source medical device doesn't mean that everyone can still screw everything open and change components. No, it's still fixed. And if you do that, then you just lose your approval. Of course. No, so it's a timestamp here. But this has to go with some versioning strategy as well. And again, discussions I mentioned already, Matrix is the future for us. Okay, we don't know where this journey will go. At the moment, we are just like separate words between public space research and then the products, which is more in the private space, and how you transition from one to the next is extremely difficult. Here it's a chance to actually, we don't know like where this border is, like what can be done in which space, and how can we more effectively work together. And I think this is a huge opportunity here to do it in an open source way, which of course we still need to explore because it hasn't really been done yet. But the research community that keeps an open source core of an MRI system is fantastic. And if some products develop out of it that help patients, that's even more fantastic. So looking forward to see how this evolves. So coming back to the timeline, next step. So next year we hope to finish this, or we have to finish this version 2. Not hope, have. Another thing that we also started to move finally is to go to for open source imaging, to go to a more NGO status, because it got a complexity that might help us, and also maybe create some more resources to push the whole idea forward. this business ecosystem will be interesting. So there are some companies interested in some software modules, but also some hardware parts. If that is available, that you basically have the option, okay, I can build, or okay, I can buy. I think this would extremely help to scale it up. And then again, the target is of course the clinic at some point. Yeah, just to set a date in 3 years sounds good. Let's try to reach that and then to really create the impact. And the interesting part is that the infrastructure that we are setting up here, I don't think it's limited necessarily to low field. I think low field is nice to start, but I think many things can then be also done or transferred to other field strengths, which would have even more impact. Yeah, so but this is a good start, and we need to demonstrate that it works first, of course. All right. With that, I'm done. Here's some resources: open source imaging, MR Hub. There are a lot of projects, open source projects in there. The GitLab page I mentioned, mriforall.org. AIM is this project website. This was the Open Lab I was talking about briefly, and then we have a recent review paper with a lot of resources, etc. There are long tables with the projects, and since the paper is static, we also generated a more dynamic version of this in GitLab, so you can also add your projects or change it. And we actually want in the long run to create a more or a better open source documentation standard of the projects that are out there through this. And if you're interested in any of that, just join us or join this community or whichever community. Yeah, extremely helpful. Many more ideas that what we can do, and but it all goes in the right direction, and look really happy to see all these fantastic results that happened in the last years, and looking forward to see what comes next. So thanks for your attention, and I'm happy to answer questions.